you hopefully have a little intuition now on what a double integral is, or how we go about figuring out the volume under a surface. So let's actually compute it, and I think it'll all become a lot more concrete. So let's say I have the surface z, and it's a function of x and y, and it equals x y squared. It's a surface in three-dimensional space, and I want to know the volume between this surface and the xy plane, and the domain in the xy plane that I care about is x is greater than or equal to 0 and less than or equal to 2, and y is greater than or equal to 0 and less than or equal to 1. And let's see what that looks like, just so we have a good visualization of it. So I graphed it here, and we can rotate around. This is z equals xy squared, and this is the bounding box, right? X goes from 0 to 2, y goes from 0 to 1. So we literally want this, you could almost view it the volume, well, not almost, exactly view it as the volume under this surface, between this surface, the top surface, and the xy plane. And I'll rotate it around so you can get a little bit better sense of the actual volume. We rotate it. Now I should use the mouse for this. So it's this space underneath here. It's like a makeshift shelter or something. And I can rotate it a little bit. So you can see whatever's under this, between the two surfaces, that's the volume. Whoops, I flipped it. There you go. So that's the volume that we care about. Let's figure out how to do it, and we'll try to gather a little bit of the intuition as we go along. So I'm going to draw a not as impressive version of that graph, but I think it'll do the job for now. Let me draw my axes. That's my x-axis. That's my y-axis. That's my z-axis. X, y, z, and we're going, x is going from 0 to 2, let's say that's 2. Y is going from 0 to 1. And we're taking the volume above this rectangle, the xy plane. And then the surface, I'm going to try my best to draw it. I'll draw it in a different color. I'm looking at the picture. At this end, it looks something like this. It looks something like this. And then it has a straight line. Let's see if I can draw this surface going down like that. And then if I want where it's really good, I could shade it. It looks something like this. If I were to shade it, the surface looks something like that. And this right here is above this, right? Like this is the top, the bottom left corner. You could almost view it. So this is, let me just say, the yellow is the top of the surface. That's the top of the surface, and then this is under the surface, right? So we care about this volume underneath here. Let me show you what the actual surface. So this volume underneath here, right? I think you get the idea. So how do we do that? Well, in the last example, we said, well, let's pick an arbitrary y, and for that y, let's figure out the area under the curve. So if we fix some y, when you actually do the problem, you don't have to think about it in this much detail, but I want to give you the intuition. So if we pick just an arbitrary y here, so on that y, we could think of it, if we have a fixed y, then the function of x and y, you can almost view it as a function of just x for that given y. And so we're kind of figuring out the value of this, of the area under this curve. Right? You should view this as kind of an up-down curve for a given y. So if we know a y, we can figure out then, for example, if y was 5, this function would become z equals 25x, right? And then that's easy to figure out the value of the curve under. So we'll make the value under the curve as a function of y. We'll pretend like it's just a constant. So let's do that. So if we have a dx, that's our change in x. And then our height of each of our rectangles is going to be a function. It's going to be z. The height is z, which is a function of x and y. So we can take the integral. So the area of each of these is going to be our function, xy squared. I'll do it here because I'll run out of space. Xy squared times the width, which is dx. And if we want the area of this slice for a given y, we just integrate along the x-axis, right? We're going to integrate from x is equal to 0 to x is equal to 2. From x is equal to 0 to 2. Fair enough. Now, but we just don't want to figure out the area under the curve at one slice for one particular y. We want to figure out the entire area of the curve. So what we do is we say, okay, fine. The area of this under the curve, not the surface, under this curve for a particular y is this expression. Well, what if I gave it a little bit of depth, right? If I multiplied this area times dy, then it would give me a little bit of depth, right? We'd kind of have a three-dimensional slice of the volume that we care about. I know it's hard to imagine. Let me bring that here. So if I had a slice here, this is what we just figured out, the area of a slice, and then I'm multiplying it by dy to give it a little bit of depth. So you multiply it by dy to give it a little bit of depth. And then if we want the entire volume under the curve, we add all the dy's together, take the infinite sum of these infinitely small volumes really now. And so we will integrate from y is equal to 0 to y is equal to 1. I know this graph is a little hard to understand, but you might want to rewatch the first video. I had a slightly easier to understand surface. So now how do we evaluate this? Well, like we said, that you evaluate from the inside and go outward. And it's almost like taking like a partial derivative in reverse. So we're integrating here with respect to x. So we can treat y just like a constant, like it's like the number 5 or something like that. So it really doesn't change the integral. So what's the antiderivative of xy squared? The antiderivative of xy squared, I want to make sure I'm color consistent. Well, the antiderivative of x is x to the 1/2, x squared over 2. X squared over 2, and then y squared is just a constant, right? And then we don't have to worry about plus c since this is a definite integral. We're going to evaluate that at 2 and 0. And then we still have the outside integral with respect to y. So once we figure that out, we're going to integrate it from 0 to 1 with respect to dy. Now what does this evaluate? We put a 2 in here. If you put a 2 in there, you get 2 squared over 2. 2 squared over 2. That's just 4 over 2. So it's 2y squared. 2y squared minus 0 squared over 2 times y squared. Well, that's just going to be 0, so it's minus 0. I won't write that down because hopefully that's a little bit of second nature to you. We just evaluated this at the two endpoints, and I'm short for space. So this evaluated at 2y squared, and now we evaluate the outside integral. 0, 1 dy. And this is an important thing to realize. When we evaluated this inside integral, remember what we were doing? We were trying to figure out for a given y what the area of this surface was. Well, not this surface, the area under the surface on this kind of, for a given y, right? For a given y, that surface kind of turns into a curve. And we've tried to figure out the area under that curve in the traditional sense, right? So this is going to be this ended up being a function of y. And that makes sense because depending on which y we pick, we're going to get a different area here because obviously depending on which y we pick, the area, kind of a wall drops straight down, that area is going to change. So we got a function of y when we evaluated this, and now we just integrate with respect to y, and this is just plain old vanilla definite integration. What's the antiderivative of 2y squared? Well, that equals 2 times y to the third over 3, or 2/3 y to the third. We're going to evaluate that at 1 and 0, which is equal to, let's see, y 1 to the third times 2/3, that's 2/3, minus 0 2/3 times 2/3. Well, that's just 0. So it equals 2/3. 2/3, if our units were meters, it would be 2/3 meters cubed, or cubic meters. But there you go. That's how you evaluate a double integral. There really isn't a new skill here. You just have to make sure to keep track of the variables, treat them constant when they need to be treated constant, and then treat them as a variable of integration when it's appropriate. Anyway, I will see you in the next video.